Our last video in Chapter 13 will be about using the line formula from the plots to solve problems. We're going to be using the integrated rate laws, solving problems for concentration, time, the rate constant, and the half-life. These are the three different integrated rate law sets for 0, 1, first order, and second order. Remember that these will fit the pattern y is equal to mx plus b. Y being a point on the y-axis, x and a point on the x-axis. M is slope, and b is the y-intercept. A couple of things to note here, if we look at just a sketch of a graph. In the case of 0 and first order, you have a negative k, which means the slope is going in this direction. So when you're solving for k, don't forget you're taking a negative of a negative, because the value of k will always be positive. K is a positive number, because you have shown in your line formula here negative k. So a negative of a negative will be a positive. Let me erase for just a moment. Something else we need to make sure and define. The y-intercept, b, and I'll just abbreviate that, is the place where the line crosses the y-axis. Oh, that's not a very good line there. Right, so let's look at a plot here. Right, the y-intercept is this place where the line crosses y when y is equal to when x is equal to 0, excuse me. So in some cases, in this particular, in all of these graphs, we're looking at a sub 0. Let me erase for just a moment and remind us about a sub 0. This is initial concentration when time equals 0, and again that's the x axis on these plots, so that makes sense. So in some cases we may be solving for initial concentration. In some cases we may be solving for A after a set amount of time. Also notice the half-life expressions, and this is different for each plot, of course. The half-life, remember, is important when we think about drug delivery and time of consumption, rate of metabolism in the body. We also see it being important in nuclear chemistry, which is something we'll talk about later in the semester. All right, let's look at two example problems using the integrated rate law. The first problem tells us we have a reaction of A going to products B and C, and this was monitored as a function of time. A plot of natural log A versus time yields a straight line with a slope of negative 0.0045 per second. So we're going to solve for rate constant, write the rate law, find the half-life, and then work a problem with the integrated rate law line formula. All right, so first one, what is the rate constant? If we remember, y is equal to mx plus b. In the case of a first order plot, we have ln a is equal to negative k x, well, that's time, pardon me. Let me erase that. Whoops. Time plus natural log of A sub 0, initial concentration. Right, so the rate constant is K, so we want to find this value. We're already told what the slope is. So M is equal to negative 0.0045 seconds. The only thing that I need to do is to remove the negative. On the previous slide I said, remember that K will always be a positive value. So K is equal to 0.0045 per second. Now I can write my rate law. The second part here, I'm told it's first order, so rate is equal to K times the concentration of A. And then I could go ahead and plug in my value for K. Rate is equal to 0.0045 per second times the concentration of A. And that is the rate law. All right, for the next couple of problems, let me erase for a second here. All right. What is the half-life? The half-life formula from that chart, T 1/2, for a first order function is 0.693 divided by K. So in this case, it's 0.693 divided by 0.0045 per second. Right, so I take 0.693 divided by 0.0045, and because I'm dividing by seconds, my answer will be in seconds, 154 seconds. Right, so remember the half-life is the time needed for 1/2 of A to react. All right, so last problem. I'm going to be using the integrated rate law, so let me erase here for just a minute. We can plug and chug into it. All right. If the initial concentration is 0.250 molar, what is the concentration after 225 seconds? Right, so I have initial concentration, which plugs in there, and I have time, which goes there. I know what K is because I solved for that previously, and so I just need to plug and chug. ln A is equal to negative 0.0045 per second times 225 seconds plus ln 0.250. All right, so I need to go ahead and multiply these, and those seconds will cancel out. And I get negative 1.0125 minus, I'll go ahead and resolve the log here. I'm getting negative 1.3863. Right, so that means that ln A is equal to negative 2.398. And so in order to find A, I need to divide both sides by ln. And when we do that, we get the inverse natural log, or e, to the negative 2.3988. And so if I'm using a graphing calculator, I put in inverse log, or e, first, then the change sign, and then the value of 2.3988, enter. If I'm using a small calculator, like one of my Casios, I have to put the number in first, change sign, and then inverse natural log. When I do that, I get a final answer of, I'll write it up here, A, the concentration of A is equal to 0.0908 molar. So let's think about this. I know that I started with 0.25. I know that the half-life is 154 seconds, and this is more than that. So I would expect more than 50% to be gone. 50% would be 0.125, and this number is less than that, so that makes sense. Right. Okay, so we solved all parts of that problem. Let's look at another example. All right, in our second example problem, we've got 4 parts to this, and so I'll work them one at a time. I think the first one was supposed to be, what is the half-life? T1 half. So let's do that first. We're told that it's first order, and the rate constant, or K, is 1.42 times 10 to the negative 4th per seconds. So T1 half is equal to 0.693 divided by 1.42 times 10 to the negative 4th per second. Right, and so I do the math there, and I end up with 4,880 seconds if I'm looking at 3 sig figs, like my given there. All right, part B. How long will it take to decrease to 25% of the initial concentration? All right, so I'm solving for T in this particular case. And I'm asked about 25%. What you can do here is you can say that A sub 0, initial concentration, is 1. And just pick a number. It doesn't matter what it is. A would be 0.25, right? So it just has to be 25% of whatever initial concentration is. I could make it 10 and 2.5, 125. It doesn't matter, as long as I have the proportion correct. All right, so I'm going to rearrange my formula. ln A is equal to negative kT plus ln A sub 0. So I'm going to subtract ln A sub 0 from both sides. Ln A minus ln A sub 0, and I could combine those further if I wanted, is equal to negative kT. So I'm going to divide both sides by negative k. And I get this form of the problem. ln A minus ln A sub 0 over negative k is equal to T. All right, so I need to move this up a little bit. Let me do that real quick and continue with the problem. Right, I'm going to plug and chug now. I know what K is. I know what A is, we're going to call it 1. I know what A sub 0 is. That's 0.25. And we will solve for t. So ln A, which is 0.25, minus ln A sub 0, which is 1, over negative 1.42 times 10 to the negative fourth per second is equal to t. All right, so I go ahead and resolve the logarithms here. ln 0.25 is equal to negative 1.386, and ln of 1 is 0. Okay, so I can just say minus 0 over negative 1.42 times 10 to the negative fourth per second. Right, and I go ahead and divide negative 1.386 by negative 1.42 times 10 to the negative fourth, and I get 9,760 seconds. The negatives will cancel out there. We're not going to have a negative time. All right, so that's my answer to the to that question. 9,760. Right, let's go ahead and erase for a minute and work the next problem. All right, if I can go back up here, I can look at the next one. If the initial concentration is 1, how long will it take for the concentration to decrease to 0.78? All right, so in this particular question, we're looking for time as well. And so the form of the problem is exactly the same as the one I did down below. So I'll go ahead and scoot down below again. And we're going to use this formula over here in black. ln A minus ln A sub 0 over negative k is equal to t. All right, so plugging those in, ln 0.780 minus ln 1 over negative 1.42 times 10 to the negative fourth per second is equal to t. And I get negative 0.248 over negative 1.42 times 10 to the negative fourth per second. And for this one, I'm getting 1,746 seconds. All right, so there were two problems, both solving for time. Let's look at our last one. I'll go ahead and erase for just a minute. And go back up here. If initial concentration is 0.150 molarity, what is the concentration after 200 seconds and 500 seconds? All right, so let's see, let's scoot down here and give ourselves some room. All right, in this particular case, if I'm looking at ln A, is equal to negative kt plus ln A sub 0. In this case, I'm solving for ln A, and so I'm just going to plug and chug into the formula. Negative 1.42 times 10 to the negative fourth per second times 200 seconds plus ln 0.150. Right, and when I multiply the 200 times negative 1.42 times 10 to the negative fourth, I get negative 0.0284 minus 1.897. I get ln A is equal to negative 1.925. And then I'm going to take the inverse log. So A is equal to e to the negative 1.925. When I resolve that, I get 0.146 molar. Okay, and that's my answer for the first part of that. I could do the 500 second example, but that particular one works just the same way. I can go ahead and tell you that the answer to that is 0.140 molar if you want to go through the math on that one as well. We'll do some more examples in class in Activity 13.4, and I will also work some examples as well, either Friday or Monday.